This video highlights the residual stress in materials and the Williamson Hull plot. Introduction of residual stress. Residual stress is stress that remains in the material after the external force that caused the stress has been removed. Next, stress is defined as force per unit area. From the image below, after the load is removed, the object retains its shape despite residual stresses. XRD cannot directly determine stress, but uses diffraction peaks to calculate strain. Full width at half maximum, FWHM, of the peaks is used to determine microstain through WH plotting. Next, for the stress removal method, heat treatment such as annealing is used. From the heat treatment graph, peak shifts and broadening indicate strain effects. XRD measures strain in lattice planes through shifts in the diffraction peak, as stress cannot be determined directly. According to Bragg law, D is inversely proportional to theta. These shifts, recorded as a function of the sample's tilt angle. Residual stress is then calculated using elasticity theory. The peak profile is influenced by instrumental contributions, include parameters like slits and detector arm length. Crystallite size affects peak broadening, analyzed using full width of half maximum and Sherer length. Peak broadening also due to microstrain, including non-uniform strains, faulting, dislocations, antiphase domain boundaries, and grain surface relaxation. Additionally, solid solution inhomogeneity and temperature variations contribute to peak broadening. The Williamson Hull plot is a graphical method used to determine parameters like crystal lattice strain and crystallite size from XRD data. It uses Sherer Formula by accounting for both size-induced and strain-induced broadening of diffraction peaks. The Williamson Hull plot is used because it separates size and strain effects, quantifies microstrain, determine crystallite size, assess material quality and investigate processing effects. The formula for total broadening is the sum of crystallite size broadening and strain broadening. The crystal size broadening is the product of shape factor and X-ray wavelength per crystallite size cos theta. The strain broadening is the product of force sine theta and strain per cosine theta. Theta is the peak position. To construct the WH plot, we must collect XRD data, determine the full width half minimum of the peaks, calculate the values for the axis, and plot the graph. The graph is interpreted using the slope and the y-intercept. The limitations of using the WH plot are assuming uniform distribution of strain and crystallite size. The WH plot can also be sensitive to experimental errors and data quality. From the derived WH equation, we can plot the graph, the x-axis and y as is shown. The slope of the graph is the microstrain. Here is an example. Using the data of 2 theta and FWHM, we can obtain the other data needed to plot the graph as shown. From the graph, we can get the crystallite size and the strain. The WH plot can be used to determine crystallite size in nanomaterials, estimate residual strain in materials, and help us understand the relationship between material processing and structural properties. Thank you for watching.